New pictures captured by the James Webb Space Telescope have staggered specialists. As opposed to merely extending our view of the universe, these pictures have uncovered an unsettling reality: our continuous cognition is deficient in grasping the possibilities of the universe in its nascent stages, where the Big Bang Theory seems to reach its limits. This revelation compels us to contemplate new theories regarding the universe's origins. This new discovery challenges even the most experienced researchers to re-examine the Big Bang and the intricate details of this cosmic event. Let's explore the concept of the Big Bang itself. Contrary to popular belief, the Big Bang was not an explosion in pre-existing space. Rather, it was space itself that began around 13.8 billion years ago alongside matter and time. A singularity in physics and cosmology describes a point where gravity is so intense that the curvature of spacetime becomes infinite. Today, billions of years after the universe's inception, we see that our vast cosmos is part of a grand cycle. For specialists, this represents a key aspect of the universe's very existence. It is clearly in continuous expansion. However, it is crucial to understand that the universe is not expanding into pre-existing space. Rather, space itself is constantly growing in size. According to current theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Ages. This was when the first luminous celestial objects coalesced to form mature galaxies. However, the rapid formation of these galaxies remains a perplexing mystery. A wealth of data emerged from the initial images captured by the James Webb Space Telescope in July 2022. Specialists revealed that the telescope had detected various galaxies, some of which had already existed around 300 million years after the universe's formation. However, in contrast to the massive structures formed much later, these early galaxies were significantly smaller and less massive. This aligns with the scientific model accepted by specialists, which suggests that the density of matter in the early universe was insufficient to produce galaxies the size of those observed today. What began as the identification of 6 glowing redshifted spots from the James Webb Telescope triggered one of the most significant astronomical crises in recent times. Although these newly found galaxies are similar in age to previously recorded ones, they are as large as our own Milky Way. This has created an intriguing mystery in cosmology. After analyzing a series of images captured by the near-infrared camera, specialists identified these light sources and used redshift to confirm that the light from these objects took more than 1 billion years to reach Earth. Thus, these structures existed around 570 million years after the presumed Big Bang. Upon further examination of these structures, it was concluded that the Webb telescope had captured 6 early galaxies. Surprisingly, these galaxies were so massive that they challenged conventional assumptions in cosmology. Instead of finding the expected smaller galaxies, researchers identified structures nearly as extensive as our Milky Way, despite forming in the early universe's history. If we continue analyzing the data gathered by the James Webb Telescope, we see that this gravitationally bound cluster of stars had already amassed more than 10 billion times the mass of the Sun at that time, with one possibly exceeding this threshold. However, even if this scenario is accepted, the mystery remains unresolved. If true, there would have been significantly more luminous mass in the early universe than previously estimated, posing a major problem. The identified objects contradict nearly all conventional cosmological theories. Even if just one of these galaxies turns out to be real, it would challenge previous assumptions. Additionally, the density of matter in the early universe would have to be significantly higher than previously anticipated to account for this anomaly. Another strange possibility is that these galaxies formed through an unknown mechanism that remains completely obscure to us. These revelations and discussions surrounding the Big Bang have prompted many scientists to reconsider the prevailing hypothesis. Various astrophysicists with alternative perspectives feel that their views are not being adequately represented in scientific literature. Even those who express doubts about existing theories are often dismissed. Yet even staunch proponents of the current Big Bang model are constantly confronted with unanswered questions. These include fundamental issues such as how and why the universe came into existence 13.8 billion years ago. Physicist Steven Weinberg pointed out that the concept of time as we understand it began with the Big Bang itself. Therefore, this process could not have been set in motion by something external to it. A similarly contentious question relates to the uniform distribution of radiation and matter throughout the universe. Regardless of the direction or distance we examine, we find similar densities and distributions of galaxies, nebulae, and radiation. Regular cosmologists explain this phenomenon through the theory of cosmic inflation. However, alternative theories suggest an evolving chaotic expansion in which different regions evolve at different rates. Some researchers propose that the universe might not be the entirety of existence. What if another universe existed before ours? If so, the Big Bang might be just one part of a larger cosmic cycle. According to this perspective, our universe is part of a greater structure where cycles of collapse and rebirth occur continuously. This is not the only alternative theory presented in modern cosmology. For example, in 1955, an article in NASA's Space Times argued that there may have never been a Big Bang, proposing instead that the universe has existed eternally. Another fascinating theory arises from quantum physics and string theory. Some experiments suggest that our universe might be a three-dimensional projection of a higher dimensional reality. This could mean that our reality is nothing more than a sophisticated simulation, much like a computer-generated game. While this might seem like the plot of a science fiction movie, it is linked to the Kardashev scale, which measures a civilization's technological advancement based on its ability to harness energy. If an advanced civilization could fully harness the energy of an entire universe, it might create a perfect simulation indistinguishable from reality. Investigating the depths of cosmology leads us into a realm of profound mystery and scientific inquiry. The James Webb Space Telescope's latest images have reignited discussions about the nature of our universe, challenging established theories and prompting scientists to reassess fundamental aspects of cosmology. As technological advancements and theoretical breakthroughs continue, our understanding of the cosmos will evolve, whether exploring black holes, distant galaxies, or the nature of reality itself. Each discovery brings us closer to unraveling the universe's secrets. As Carl Sagan once said, somewhere something incredible is waiting to be known. This sentiment encapsulates the essence of scientific exploration, a continuous journey of revelation, wonder, and enlightenment. As we push forward in our understanding of the universe, new revelations continuously challenge our perspectives on cosmic evolution and the fundamental principles governing existence. The James Webb Space Telescope, JWST, has already provided an unprecedented glimpse into the early universe, revealing structures that defy conventional models and prompting scientists to reconsider the established framework of cosmology. One of the most pressing questions that emerge from these findings is the nature of dark matter and dark energy. These two elusive components make up the vast majority of the universe's mass-energy content, yet their true nature remains a mystery. Dark matter is believed to be responsible for the gravitational scaffolding that allows galaxies to form and persist, while dark energy drives the accelerating expansion of the universe. The discoveries made by JWST suggest that the distribution and behavior of these unseen forces may be even more complex than previously assumed. Furthermore, the discovery of massive galaxies in the early universe raises significant questions about the process of star and galaxy formation. Traditional models suggest that galaxies should have grown more gradually over billions of years, accumulating mass through mergers and star formation. However, the existence of fully formed galaxies only a few 100 million years after the Big Bang implies that these structures may have assembled far more rapidly than expected. This discrepancy calls for new theoretical models that can account for such rapid cosmic evolution. Another fascinating area of inquiry is the potential existence of multiple universes. The concept of the multiverse, once relegated to the realm of speculative physics, is gaining traction as a plausible explanation for some of the inconsistencies observed in cosmological data. According to certain interpretations of quantum mechanics and string theory, our universe may be just one of many, each governed by different physical laws and constants. If true, this would revolutionize our understanding of reality itself and open up new avenues for exploring the nature of existence. The implications of these discoveries extend beyond the realm of theoretical physics and into the broader philosophical and existential questions about our place in the cosmos. If the universe is indeed part of a grander, interconnected multiverse, what does that mean for our understanding of life, consciousness, and the nature of reality? Are there other intelligent civilizations exploring their own cosmic frontiers, pondering the same mysteries that captivate us?